Okay, so we'll take some applications of um, derivatives. So till now I have been saying some function of x, function is like this, function is like that. But when you are doing physics problems, that function would mean something. Okay, so that f of x could be giving you the position as a function of time. Okay, so let's take a physical problem. You have some object here, okay, and it is moving on the straight line along x-axis. So its location on the x-axis I will denote by x. So here why it is giving, should be giving white, no? Okay, so that is x. So this object is going along, moving along x-axis, whichever way it is, I am going to specify. So as time passes by, this guy will be at some location. Okay, so the function which gives its location at time t is x of t. Okay, so earlier we were saying f of x, and x was the independent variable. Now t is the independent variable, and f is what is position now. Okay, and that I denote by x. Is that okay? So for example, f of x of t could be .5 meters. So that's a constant, meaning as time passes by, this guy is just sitting at that location 0.5 meters. It does not move. Okay, this is a stationary object. Okay, let's keep checking. Is the dimension correct on both sides? That's meters, that's the unit of length, that's length, so that's fine. Okay, that's stationary object. Now let's take a function. So suppose object is moving moving along x-axis, and its location at time t is given by okay, it is linear in t. So x of t is equal to t. Is this fine? It's not fine, because here t has dimensions of time. So you will say, okay, 2 seconds, 3 seconds. But left hand side is length, it's the position. It has dimensions of length, 3 meters away, 2 meters away. So this is not dimensionally meaningful. So I will supply something here which will make it dimensionless. So let's say 2.0 per second, meter per second. So if I multiply this number, this right hand side now has dimensions of length. See, let's try putting t equal to some seconds. So that's number of seconds. Let's say t equal to 5 seconds. So seconds divided by seconds is, the seconds cancel and you are left with meters. So that is meaningful. So right hand side has now correct dimensions. Okay, so this is meaningful. Now this is a linear dependence, right? So this object has linear dependence in time, or its position, not object, position of the object has linear dependence on t. Is that okay? Linear because t, there is t to the 1, t to the power 1, and you know that such functions give you a straight line. You remember this? Y equal to mx plus c. So instead of y you have x, and instead of x you have t. Okay, right? You understand that? So That is how this is. Even if I were to add some constant here, it still remains a linear thing, right? So let's add some number. Can I add 5.0? Does that make sense? No, it does not make sense. Because this is dimensionless. That has dimensions of length. Left hand side has dimensions of length. So this has to have dimensions of length. What should I write?
Meters.
Is it a problem if I write kilometers? No problem. Because that is 5,000 meters. Okay? So that is fine. Let's look at another particle or another object whose position has quadratic dependence. See, I am free to choose. I decide which way it will move. Okay? That's my decision. I say this guy moves like this, so it moves like this. You might ask, how will you make it move like that? That's a separate question. That might be very, very difficult or impossible. But who stops me from imagining? So I'm imagining certain behaviors. I'm saying, okay, this object moves like this, it never moves. It moves like this. Okay? So let's take quadratic dependence. Okay? So I want something which has t square, but quadratic means you are allowed to have t and constant also, right? So the maximum should be square. So t square, t plus some constant, and as I said, that constant should have the dimensions of length, because left hand side is giving you position. Position is some distance away, that's length. So let's say we choose it to be 2.0 meters. Okay? So let's supply some. So this is not correct. This is length. This is time square. Dimension of this is time square, and I should have each term have dimensions of length. You cannot have one term dimension of length and you add to it as something which has dimensions of time. That's meaningless. Okay? So I should ensure that each term has dimensions of length. So this is length square, time square. I want length. So I should have length divided by time square. What I supply here. So let's say I put 2 meter per second square. Let's 2.0. Does that make sense? Time square denominator, that's time square, that's gone, length. So that makes sense. How about here? This time it is just time, so I should have something like that. Not times second square. It should be seconds. Right? And it is not necessary that I should have meter over second square. I could have kilometer over second square also, or meter over hour square. They are all fine. Okay? So that's one kind of thing you can have. Let's take some other examples. Let's say I want this guy to be moving like this. Is this fine?
Over meter.
So,
Over second, sorry, not meter.
yeah. So, left hand side is, as I said 1,000 times already, length, but right hand side is sine. Okay? Now sine is what? Sine is, remember, perpendicular over hypotenuse. This ratio of two lengths, and ratio of two lengths is dimensionless, right? Because length divided by length is dimensionless. Is that okay? So sine function is a dimensionless object. And the argument of what is the argument of sine function? Sine of x, let's say sine of theta. The theta is angle. Angle is dimensionless, right? So it is the arc length divided by the radius. Length divided by another length, that's dimensionless. So the argument, when we say argument, it means sine of this. This is called the argument, okay? The argument here should be dimensionless, but here the argument has dimensions. So let me divide by something so that it makes it dimensionless. So let's say I say 5.0 seconds. Is the argument of sine dimensionless now? It is. So this makes sense. Does that make sense? No, it does not make sense. Now what you have on right hand side
Into meter.
is dimensionless. So into something, no, don't say into meter. No.
Into something.
In times a constant which has dimensions of length. So let's say this time I want 5.1 kilometers. Does that make sense? That makes sense. So you have an object moving like this. Is that okay? Okay, one more example. You could have an object. So I want an object to move like this. 5.1 kilometers per second times sine of t over 3.0 seconds. Okay, that looks good. That's something like what I have here. Sorry, I have put kilometer. That's wrong. Okay, plus I want something quadratic. So t square, and I should have something which makes the dimensions correct, and this makes the dimensions correct. Is that okay? I could have similar things here. Okay, so now let's make some connection with the derivatives. Okay. So let's recall what speed is. No, not speed. I want velocity. So suppose a particle or an object is located at time t at position x. Okay? Or let's say I am given the position of the particle or the body as a function of time. So what is the velocity? Velocity is where it is located at time t plus delta t. Okay, let me make it more precise. What's the velocity of that object at time t? It is where it is located at time t plus delta t, where delta t is small, minus position at time t. Okay, so it is as it is moving in time. You want to know the velocity now, so what you do is you ask where it is located after time delta t, or before a time delta t is also fine. So in that case delta t would become negative. Remember, the slopes from both the sides should match. So my result should not depend on whether I am going from positive times or negative times. Okay, I mean not positive, negative. Either I am approaching this time from earlier times, or I am approaching this time from later times. Okay, divided by delta t. Right, that's the average velocity in the time interval delta t. Is that, you know this, right? So to know the velocity at time t, I should take the limit. Remember that? But what is that called? That's called the derivative of the function. If instead of x, if I had written f, and instead of t I had written x, so you would have written df over dx. So this is now d over dt of xt. Do you agree? So velocity is just the derivative of position. Is that okay? Good. If that is okay, that is very good. So let me write again. Velocity at any time t is d over dt of x of t. What is acceleration? Okay, I am still imagining the object is moving along a straight line which I call x. Okay, it's a one-dimensional motion. So what's the acceleration? Acceleration is rate of change of velocity with time. So it is v at t plus delta t Is it too fast or is it, it's okay? Is that okay? But what is that? That's the derivative of velocity. But what's velocity? Velocity is derivative of position. So it is the derivative of the position, and you again take the derivative, right? So derivative of the position. So that's the second derivative. Agreed? That's the second derivative, or we have also been calling this as, I hope I introduced this notation. Did I introduce this notation? Did I introduce this notation? Are you sure?
Yes, you did.
Okay. If I did, very nice. So what's acceleration? Acceleration is the second derivative of position as a function of time. Okay, good. So now I'll give you some examples. So let's take this. So I'll give you one exercise, you do it and tell me what's the velocity of this object. So an object is moving along x-axis and its position as a function of time is given by this. It's, let's take a linear thing. No, not linear. Let's take a constant thing. So I say 5.0 meters. What's its velocity? 0. You can already see it's staying always at 5 meters. So it's not moving, so its velocity is 0. Or if you take a derivative of a constant is 0. So velocity is 0. Okay. So v at all the times is 0. Let's take another example. Okay, I hope you understand that I am adjusting the dimensions. Okay. Okay, let's find out its speed at some time. What's its speed at 2 yeah, let's say speed at 2 seconds. Can you find it out? Done? 2 meters per second. Very nice. Because when you take the derivative of this, which gives you the speed, derivative of constant is 0.
And the is 2 meters per second into 1 is equal to 2 meters per second.
Very good. So when you take the derivative of this, it becomes derivative of this becomes derivative of this plus derivative of this. Derivative of that is 0. And derivative of this is a constant, so it comes out 2.0 meter per second times the derivative of t. So d over dt of t is 1. So you get okay. So we'll remember it like this. And you can imagine whatever numbers you put here does not matter. That number is going to come here.
V of 2s.
Yeah, even that is correct. V of t is this. So V of 2. If it is, see, it's a constant speed, right? So no matter at which time you calculate, you get the same answer. Because at that time I wanted to ask what's the speed at time 2 seconds. Okay, so speed at 2 seconds, 5 seconds, 10 seconds, any seconds is the same 2 meters per second. So you see here, if the position changes linearly in time, that's the linear expression, then the speed or the velocity of the object is constant. Okay, if I say speed by mistake, you should mentally replace it by velocity. I am talking about velocity. Okay. So linear dependence in time of the position gives you constant speed. Is that okay? Let's ask about its acceleration. So what's the acceleration of this object? that's 0 because it's moving with constant speed, constant velocity. So acceleration is 0. Why? Because if I take a derivative of this again, this is v of t, right? This is v of t. It's constant. So if I take a derivative of this, which is the acceleration here, then it's 0. Okay? So a linear dependence means constant velocity and 0 acceleration. We'll remember this. You should remember this. Write it down. Okay. Let's take another example. Position as a function of time is some constant, let's call it A tilde. I hope you don't dislike A tilde. A tilde is fine. Shall I put it B? A tilde is okay. A tilde t square plus bt. Okay, it's yeah, it's fine. Let's put b tilde also. Then it is okay. Plus c. Okay. So A tilde will have the right units or dimensions so that this term becomes something of dimensions length. Similarly, B tilde will have the right dimensions so that this becomes something of dimensions length, and C is of dimension length, as I showed you earlier. Now let's ask, if an object is moving with this kind of time dependence, then what can we say about its velocity and acceleration? So when I take the first derivative,
Velocity changes linearly with time and acceleration is constant.
very good. So when I take the first derivative, this will become proportional to t, this will become a constant, that will go away. So that becomes linear. Now you have a linear expression after taking the derivative. Now if I take the second derivative, meaning I take the derivative of that linear expression, that will give you a constant, which means the acceleration, which is the second derivative of position, will be constant. Is that okay? So let's do that. So let's differentiate. This is dx which is A tilde times 2t plus B tilde, correct? Now let's find acceleration. My goodness. This is what? This is d2 over dt square of this, okay, which is basically the second derivative of position. I have already taken the first derivative, so let me take the another derivative of this, which is this. So what is that? 2a tilde, it's a constant. When I differentiate t, I get 1 and this goes away. Okay? So 2a tilde. Okay, excellent. So acceleration is 2a tilde, or it's a constant. Right? I have already said a tilde is a constant. So acceleration is a function of, not really a function of time now, it's a constant. Or its functional dependency is such that it's a constant. So what I will say is 2a tilde is what? It's the acceleration. This is an object moving with constant acceleration. So what's a tilde? A tilde is acceleration over 2, it's half of the acceleration. Right? You don't know where I'm going? Okay. But you are fine with this, right? Okay. So a tilde. See, I have determined what that thing is. I'm telling that a tilde is half of the acceleration. And your object is moving with constant acceleration. Okay? So that's one thing I know. Okay, you'll be very happy when you've realized now? Good. Okay, let's go back here. Look at this expression. It says velocity at time t is this. Now what I'll do is I'll say put t equal to 0. And you know why I want to put t equal to 0? Because that term will go away. If t equal to 0, this goes away. At t equal to 0, the left hand side is the velocity at time t equal to 0. Let me give it a symbol. So I'll say velocity at time t equal to 0, let's call it v naught. So if I take here velocity at time t equal to 0, which is v naught, this goes away, is b tilde. So what do I have? Velocity at time, now everything will start happening. Velocity at time t equal to 0, vt0, which is v naught, is equal to t equal to z goes away, it's b tilde. Now you understand why I had put tildes. Otherwise, if I had put a here, the notation will be gone, right? It will be destroyed. So v naught is b tilde. So in this expression, what's b tilde? B tilde is v naught. Now let's go back to the position itself and take that thing at time t equal to 0. So what's the position at time t equal to 0? It may not be at the origin. It might be a little away from the origin, this way or that way. Okay, so let's call as x naught. So at time t equal to 0, this is x naught, that's 0, that's 0, that's c. So c is equal to x naught because other two terms are 0, right? So this is equal to c tilde. I should have put a tilde. It would have looked nicer. Okay, so you see, what do I have here? I have this relation, and this relation. Okay, see here, you can write. I'll give you time to write. Is that okay? So if let's take this expression and substitute these things. So I have position of a particle moving along a straight line whose position depends on time in a quadratic manner to be this. Now I have identified the meaning of these constants. See, you could give me a general thing, right? You say, okay, that should be 2 point this thing, that should be 5 point whatever units, this is this. But now I know what those constants mean. That constant is actually acceleration over 2. That's the acceleration of that thing, and acceleration is constant, so I'm not going to put a of t, I'm going to just put 2. What is b tilde? B tilde is v naught. What's c tilde? C tilde is x naught. Okay, so I'll write it like this. Okay, if you want to. So you see, you might recall this formula. S is equal to ut plus half at square, or S is equal to S naught plus ut plus half at, that's this formula. Okay, and you have most likely already seen that formula earlier, but you might have not done this kind of derivation, but I have derived this. Okay, but you see how we have started. I said, okay, let's look at some functional dependence of position like this on time, and then I arrive here. Is it okay? Tired? Okay, so then stop. Let's stop here.